Welcome to The Explainer. I'm absolutely thrilled to have you here today. If you're a focused learner looking to completely demystify the mathematics, well, you're in exactly the right place. Today, we're tackling a concept that forms the absolute backbone of arithmetic and algebra, but still manages to trip people up. I'm talking about rational numbers. We're going to strip away the complex jargon, look at some really clear visual concepts, and just decode the whole thing together. Let's jump right in.
Okay, here's our roadmap for today. 1. Meet the rational numbers. 2. Visualizing and comparing. 3. Math rules and core properties. 4. Exploring the infinite space. 5. Real-life applications. And 6. Let's review with a Q&A session.
Section 1. Meet the rational numbers. The foundation.
So let's start with a really fundamental question. What exactly is a rational number? You know, you've definitely heard the term before, maybe back in school or just in passing, but what actually separates it from a whole number, an integer, or just your regular everyday fraction? Well, here's the absolute golden rule. A rational number is quite simply any number that can be expressed as a over b, like a fraction. So think 3 over 4 or maybe negative 5 over 2. Now, a and b must be integers. Those are your standard whole numbers and their negative counterparts. But notice that crucial last part. b, the denominator at the very bottom, can never, ever be equal to 0. Why? Well, in math, dividing by 0 is completely undefined. It's literally a fundamental law of the universe you just can't break. If you try to divide a pizza into 0 slices, the whole thing just kind of breaks down, right? So b is never 0.
Now, just like language has grammar rules, rational numbers have what we call a standard form, just to make them universally understood. It's essentially about cleaning up the fraction. Step 1. Always make sure that bottom number, the denominator, is positive. If you've got a negative down there, just move it up to the top. Easy. Step 2. Divide both the top and bottom by their highest common factor until they're co-prime. That just means they don't share any common factors other than 1. For example, if you're looking at 48 over 72, you divide both by their highest common factor, 24, reducing it cleanly down to 2/3.
And that brings us perfectly to equivalent rational numbers. I like to think of equivalent numbers as wearing different outfits, but being the exact same person underneath. You can multiply or divide the top and bottom of a rational number by the exact same non-zero number, and you haven't actually changed its core value at all. Like 1/2 has the exact same value as 2/4, which is exactly the same as 4/8. They are identical values, just walking around in different disguises.
Section 2. Visualizing and comparing, finding their place. The number line is basically our ultimate mathematical map. And when you want to place a rational number on this map, the denominator, that bottom number, is simply your instruction manual. It tells you exactly how many equal pieces to slice your map into between 0 and 1. If the denominator is 3, you slice the space between those whole numbers into 3 equal segments. Then, the numerator, on top, it just tells you how many of those slices to count out. So to place 2/3, you slice the space into 3 and simply step forward 2 slices. Once they're placed on the map, we can talk about absolute value. This is written with those 2 straight vertical lines around the number. And here's the thing, absolute value only cares about one thing, the physical, quantitative distance you traveled from 0. It doesn't care at all about direction. Whether you walked 3 steps to the left into the negative or 3 steps to the right into the positive, your absolute distance traveled is still just 3. That is exactly why absolute value is always positive.
So how do we compare two kind of messy rational numbers to see which one is actually bigger? You just follow this foolproof 4-step method to give them common ground. First, make those denominators positive. Second, find the lowest common multiple, the LCM, of those denominators. Third, rewrite them as equivalent fractions using that LCM. Now, instead of comparing apples to oranges, you're strictly comparing apples to apples. Finally, just look at the top numbers, the numerators, and compare them directly. The larger numerator wins.
Section 3. Math rules and core properties. The laws of behavior.
Now, this brilliantly illustrates one of the most fundamental laws, commutativity. Just think of the word commute, moving around. Under addition, rational numbers are totally flexible. 3 plus 4 is exactly the same as 4 plus 3. The order simply doesn't matter. But subtraction? Subtraction is strictly rigid. You absolutely cannot just swap the order. 5 minus 3 is 2, but 3 minus 5 is negative 2. They are not the same. So commutativity works beautifully for addition, but completely breaks down for subtraction.
We can easily map out addition, subtraction, multiplication, and division against the 3 big mathematical properties: closure, commutative, and associative. What you really need to take away from this is that addition and multiplication are the friendly, flexible operations. They generally follow all the rules, allowing you to group and swap numbers around. Subtraction and division, on the other hand, are the rigid rule breakers, where order and grouping absolutely matter.
Before we leave these rules, we've got to know our identities. The additive identity is 0, because adding 0 to any rational number doesn't change its core identity. The multiplicative identity is 1, for the exact same reason. And then we have the multiplicative inverse, which you probably know as the reciprocal. This simply means flipping the fraction upside down. If you have 3/5, the reciprocal is 5/3. Multiply them together, and the product is always exactly 1. In fact, dividing by a rational number is actually just multiplying by its reciprocal. It's a fantastic little shortcut.
Section 4. Exploring the infinite space, the density of rational numbers. Okay, imagine using a giant magnifying glass on the number line. If you take two whole numbers, let's say 1 and 2, you know for a fact there are no whole numbers between them. But with rational numbers, this mind-bending concept of density takes over. If you take any two rational numbers, even ones sitting right next to each other, like 1/10 and 2/10, and you look closer, you will find an uncountable infinite number of rational numbers hidden in the tiny gap between them. You can literally zoom in forever.
So practically speaking, how do we find these hidden numbers? Well, here's a really great trick for your homework. Say you need to find numbers directly between 3/5 and 4/5. First, ensure they have the same denominator. They do. Then, just multiply the top and bottom of both fractions by 10. Magically, 3/5 becomes 30/50ths, and 4/5 becomes 40/50ths. You've just artificially expanded the gap. And now you have 9 whole numbers, 31, 32, all the way up to 39/50, sitting perfectly right between your original two values. How cool is that?
Section 5. Real-life applications, math in the real world.
Let's transition out of pure theory. Imagine a highly practical construction problem. Let's say you're paving a rectangular hall. The length and breadth of the hall are measured in mixed rational numbers, something like 21 3/4 meters. And the tiles you're using, they're also fractions of a meter. To find out exactly how many tiles you need, you first have to calculate the total area by multiplying those rational numbers, and then divide that total area by the area of a single tile. By using that reciprocal trick we just talked about, flipping the fraction to multiply instead of dividing, you can find the exact number of tiles needed without ever touching a calculator. This is how math literally builds the world around us.
Section 6. Let's review. Q&A session. Testing your knowledge.
All right, it's time for a chapter checkup. Which of the following is the additive inverse of -5/6? Is it A, 6/5, B, -6/5, C, 5/6, or D, 0? I'm going to give you a brief mental pause to lock in your answer.
And the correct answer is C, 5/6. Remember our core property rule here. A number plus its additive inverse must always bring us right back to the additive identity, which is 0. So -5/6 plus a +5/6 equals exactly 0. Great job if you nailed that one.
Okay, let's try one final, slightly tricky question to challenge your memory of those properties we went over. The multiplicative inverse, or the reciprocal, of a negative rational number is A, a positive rational number, or B, a negative rational number.
The correct answer is B, a negative rational number. Remember, when we find the multiplicative inverse, all we're doing is flipping the top and bottom numbers. We absolutely do not change the sign. Flipping a negative fraction preserves that negative sign completely. Well, you've done an incredible job following along today. From the absolute basics to exploring the infinite density of numbers sitting quietly between 1 and 2, you now have a totally solid grip on rational numbers. But I want to leave you with one final thought based on that magnifying glass analogy we used. If an infinite universe of rational numbers can exist within the tiniest fraction of a space on a simple number line, where else in your life might invisible infinite details be hiding right in plain sight, just waiting for you to look a little closer? Keep learning, keep questioning, and I will see you in the next explainer.